So now let's look at an example where we estimate these system parameters from a graph. We're going to find the static gain, the time to peak, the percent overshoot, the settling time for the response in the following figure. Let's find the static gain first. Okay, the dashed line x of t is 1.5, and that's going to be our input. The green line is y of t, or our output, which has a steady state value of 4. So k is equal to y of infinity over x of infinity, which is 4 over 1.5. So the static gain is 2.67. The percent overshoot is equal to the maximum value divided by the steady state value. So in this case, the peak happens at 4.5 and the steady state value is 4. So the A over B times 100 that we had before is going to be 4.5 minus 4 divided by 4 times 100. So the percent overshoot is 12.5%. The time to peak is the time that it takes in order to reach 2.5. So if we drop this down to our horizontal or our time axis, we see here that the time to peak is approximately 2.5 seconds. The settling time is the time that it takes to get within 2% of its final value and stay there. So if we come over here, 2% of our final value is going to happen. So that happens around 3.92 or 4.08. So if we estimate here that this is when it gets within 2% of its final value and stays there, then we will say that the settling time is equal to 4 seconds.
A more accurate method to find the settling time is to use the time to peak and the percent overshoot, where we find that omega d is equal to pi over tp, or pi over 2.5. So omega d is equal to 1.257 radians per second. Next, we're going to use the percent overshoot to find the damping ratio zeta. So the percent overshoot divided by 100 is equal to e to the negative zeta pi divided by the square root of 1 minus zeta squared. So 0.125 is equal to e to the negative zeta pi divided by the square root of 1 minus zeta squared. So in the next step, we're going to take the natural log in order to get rid of the exponential. So we'll have negative 2.079 equals negative zeta pi divided by the square root of 1 minus zeta squared. So next, we're going to square both sides in order to get rid of the radical in the denominator. So after you square both sides, you are going to get 4.324 equals zeta squared pi squared divided by the quantity 1 minus zeta squared. Next, we are going to cross multiply and isolate zeta. So we're going to have 4.324 times 1 minus zeta squared equals zeta squared pi squared. So we're going to add 4.324 zeta squared to both sides of the equation. So 4.324 equals the quantity 4.324 plus pi squared times zeta squared. So now you divide both sides by 4.324 plus pi squared, and you get that zeta squared equals 4.324 divided by 4.324 plus pi squared. So zeta squared is equal to 0.3046. And in the next step, you take the square root of 0.3046. So zeta is equal to 0.552. Now the damping ratio, omega d, is equal to omega n times the square root of 1 minus zeta squared. So the natural frequency, omega n, is omega d divided by the square root of 1 minus zeta squared. We now have omega d and zeta. So 1.257 divided by the square root of 1 minus 0.552 squared. So the natural frequency is equal to 1.507 radians per second. So the settling time is 4 over zeta omega n. So it's 4 divided by 0.552 times 1.507. So the settling time is 4.8 seconds, which is a little bit more accurate than the 4 seconds estimated by looking at the graph on the previous video.